measure the error by the distance to the true solution, which is typically a more reasonable way. So we want the solution more accurate. So less vectors. Now let's talk about a little bit about non-symmetric systems. So the main disadvantage of GMRS is that we have to store all the vectors, and the memory cost grows with each step. And here the main problem is not the computational complexity, but the memory. Because if you have the system with millions of unknowns, hundreds of millions, storing each, for example, 500 vectors becomes too expensive. So what to do? So one way is to do restarts. So what we need by restarts? We have a current approximation to the solution, and we want to find not the solution, but the correction to the solution. Well, this is actually a very reasonable idea of looking not for solution, but the correction to the solution, which is used in many places. For example, in the end of this section, we'll briefly mention multigrid method, and that's exactly the idea. If we don't only know a very good solution, maybe we can look for correction. But for a linear case, if you just do it like this, there is no benefit. If you know a good approximation to the solution, so what we can only do, we can rewrite our equation in terms of the equation for the correction. On the right-hand side, we'll have the residual, and then we can start solve this system of equations using GMRS. And if we start from initial guess E equal to 0, we will just build graph of subspace from the residual, from the new residual. And we forget all the previous graph of subspace. And this loses a lot of information. So it really spoils down the convergence. And for example, here we have restart 20, that's the convergence, and this is no restart. So this guy is jumping around 10 to minus 1 with no vein. In GMRS, well, starts to converge, it's already 10 to minus 5. And waiting for convergence of GM, so I have had such experience. You have a huge linear system for which you only have matrix by vector product, and you look at the convergence of GMRS. So it's not like stochastic gradient descent convergence, because there you do not even know what to measure. Okay, you can look at the accuracy, but for GMRS convergence is completely, at some point it may just go down. And since GMRS is really useful for non-symmetric matrices, the non-symmetric matrices in general have complex eigenvalues, the convergence study of GMRS is much more complicated. So you need to consider something called numerical range of the matrix. Numerical range of the matrix is just the set of all values. Okay, it won't be so easy because this thing is jammed off. range of the matrix is the set in a complex plane called numerical range. It's the set of all possible values of quadratic form. So if A is Hermitian, then eigenvalues are real. Not only eigenvalues, all the quadratic form values are real. So the numerical range is just a line from lambda min, lambda max. And you can show that every point is a point. But for general non-symmetric matrices, the numerical range is just some convex, which can show this is the point. It's just some convex set in a complex plane. So it can be some sort of something like that, even more complicated. And then the convergence of GMS depends on the properties of the numerical range and corresponding ellipses. There is a paper by Garinov, Tartishnikov, and Beckerman with I think that's the best estimate for the convergence of GMS, which we don't give here in case. So, restarts, well, it's typically nothing better that you can do, but still they can spoil convergence. So what else can be done? So the symmetric positive definite case is nice. So let's try to bring our linear system to the symmetric positive definite form. And I've told you many times that you should not use normal equations. Instead of ax equals f solve a star ax equals a star f, because you will have squared condition number. But if you rewrite this normal system of equations, or how you solve this in a smarter way, it is possible to get a method that at least converges with the same square root of condition number speed. So this was proposed by Fletcher. And the whole idea is try to get the CG type recurrent relations. So there is also a negative result. If you only use matrix by vector products and you do not use transpose matrix by vector products, it is not possible in the general case get an iterative method with short-term recurrent relations that will solve a linear system. So there is a negative result. There are no short-term recurrences for a general non-symmetric system if you only multiply matrix by vector. It's called Feiberman-Teuffer theorem, or it's also Tartishnikov-Voevodin theorem. They have somewhere in the 1980s, something like that. So so the condition number is square, so we need sort of stabilization. This method is implemented, and then how it's implemented, I will say a few words, but that's what the stock implementation of the YCG does, right? So that's clearly an unstable method. Okay? So the GMRS is at least guaranteed to be monotonic. Even GMRS with restarts cannot increase the residual. This guy doesn't care. So in the end it converges, but this is sort of very disturbing part. How it's implemented. So there are two ways that how it can be done. The first one is a bad way, and the second way is how it should be done. So we are solving a linear system with a matrix A star A, and the right hand star A star F. if we use zero vector as the initial approximation. So if we just apply CG to this matrix, then we will just run the generation of the Krylov subspace with this matrix and with this right-hand side. And since this matrix A star A has the condition number that is the square of the condition number of the original matrix, the convergence will be slow. What you can do instead, and okay, in order to multiply this matrix by vector, you need to multiply by A and you need to multiply by A star. What is a good idea? A good idea is that instead of using one Krylov subspace, we can use simultaneously two Krylov subspaces. So we start with some vectors, Krylov subspace with a bit, so they, in some way we disentangle this product into two different subspaces. In such a way, we will get better convergence. So we use two Krylov subspaces. One with the matrix A, another one with matrix A star, and they will be constructed independently of each other. So we generate two bases, but what we will need from them that these bases are not, they are bi-orthogonal to each other. So if you take the basis of, so we are not generating an orthogonal basis in each of the space, but we generate two bases such that the columns of this basis omega and the columns of the basis for A star will be mutually orthogonal. So in terms of the matrix, will be omega star V will be equal to the identity matrix. So if A is identity, we hope to get here the identity. And then, so what we had for the symmetric case. So for the symmetric case, we had Galerkin projection, right? So for the symmetric case, we had AX equals F. We minimize AX x minus 2FX subject to X equals X0 plus QC, and we get this Galerkin projection. Okay, let X0 be 0 for simplicity. We get this is Galerkin projection. And Galerkin projection is exactly the minimization of the energy functional over the Krylov subspace. So it has a clear variational formulation. This is Galerkin. What we are doing now is called, well, from mechanics, in fact, known as Petrov-Galerkin projection. Which does not have a corresponding variational formulation, but it has a clear projection formulation. So how we can get Galerkin projection out of the original equation? We had AX equals F, right? So we know that X is QC, right? So we have this equation for C. That's what we have. We now have more equations than unknowns, and one option is to, well, solve, for example, linear least squares problem, but another option is to take out of, but we assume that this system of equation is, well, more or less consistent, right? So there is a solution C such that the difference between the left side and the right side is small. So, and what we can do, we have many equations and few unknowns, so instead of solving this least squares problem in a least square sense, formulate as a least square, we might say that we want to satisfy not all the equations, but some of the equations. So one way is we just take out of all equations only some pre-selected equations, or the equations with the number 1, 2, 5, and so on, or we can take linear combination of these equations. Formally, it's just multiplication by some matrix from the left. So the Galerkin projection, we multiply this from the left by Q star. And it has variation of, but it can be just this is a consequence. So this equation is a consequence of this equation, two equations. If this holds, this also holds. But we can use another matrix to project this system of equations. So again, we have AX equals F. We have X equals W. Forgot what I was using for X hat. W was on dot, sorry. Oops. Take it. We have a lot of